All right, folks, I think we're going to get things rolling here. So on behalf of the 71 people who are on this call right now, thank you for your time and attention. My name is Mark Gillis. I am the chair of the Timber Frame Engineering Council, and I want to welcome you to our presentation this evening. It's a co-presentation of the TFEC, the Timber Frame Engineering Council, and the Timber Framers Guild. And tonight's presentation is sort of tongue-in-cheekly titled Fighting the Fake Limits on Timber Strength, 2 case studies using D245 and TFEC. It's just kind of missing from the end here, but it's TFEC 03? Yes, yeah. So today is Wednesday, December 16th. Thanks for everyone for getting their PD credits in at the very end of the year. I want to thank the Timber Framers Guild's national sponsor, Ford Panel. They're instrumental in keeping the timber frame alive and active, and are one of the reasons why we're able to do these presentations for you. I also want to thank the TFG live sponsors, which are Messick Vale and Rothoblast. They're also Timber Frame Guild company members as well. That's the introduction. I'm going to get out of that for, well, actually, I'll leave that up for a second. And just bear with me for a second, folks. We're out here. So tonight's presentation, there are 2 presenters, are Tom Nehil and Dick Schmidt. Tom Nehil is a professional engineer living and working in Kalamazoo, Michigan, where he specializes in the evaluation, preservation, and adaptive reuse of historic buildings. Tom chairs the Timber Grading Training Committee for the TFEC and is also our past chair. He's also a member of the Michigan Barn Preservation Network, Michigan Historic Preservation Network, the Association for Preservation Technology International, the International Association of Wood Anatomists, and the American Concrete Institute, among other professional organizations. I am very pleased to say that Tom is the 2020 recipient of the David Fischetti Award presented by the Preservation Engineering Technical Committee of the Association for Preservation Technology International. And it was for his paper Determining Design Stresses from Stress Values, published in Timber Framing Journal of the Timber Framers Guild, number 127 in March 2018. The intent of the Fischetti Award is to recognize an outstanding article in a peer-reviewed publication that advances the field of conservation engineering, and this was a perfect fit for that. Tom is a regular instructor at Tillers International in Kalamazoo, where he teaches wood species identification, timber frame design, and traditional stone masonry. He also taught wood identification for the TFEC and presented on topics of species identification, timber grading, and assessment of existing structures to numerous groups. And our second instructor or presenter tonight is Dick Schmidt. Dick Schmidt is currently a consulting structural engineer with Fire Tower Engineer Timber, where he focuses on structural analysis and design of timber frame structures and related systems. Previously, he served as faculty member at the University of Wyoming. Research that he and his graduates conducted in timber frame joinery formed the basis of the design standard TFEC1, our standard for the design of timber frame structures and the associated commentary. Dick is a member of the Timber Framers Guild, the Timber Frame Engineering Council, the American Wood Council, and the American Society of Civil Engineers. He served as chair of the TFEC Executive and the TFEC Technical Activities Committee, and is currently the chair of the TFEC Publications Committee. He has served as lead author for TFEC1, our first standard, since its inception in 2007, and he has authored 3 textbooks on engineering mechanics. We've got 2 amazing presenters here for you tonight. But before we begin tonight's session, I'd like to ask anyone who's on this call tonight who's interested in collecting AIA professional development credits that they enter their name and a phone number in the chat box. I trust you all know how the chat works. It's basically at the bottom of your Zoom window, there's a little function there that says chat. And if you click on that, a little window comes up and you can type in your name and your phone number. And fortunately, we're recording this session tonight, and if you put your name and information in there, we're going to collect that as a text message, and it'll be much easier for us to gather up all your names and touch base with you to get your full contact details so we can get your certificates out whenever you need them. So if you don't mind, please enter your name and a phone number and how to get a hold of you, and we'll go from there. So without further ado, I'm going to let Tom start sharing his screen, and we can start the presentation from there. Thanks, everyone.
Okay, thank you, Mark. Let's bring up the subject matter here. All right. Okay, well, thanks everybody for joining. Thanks, Mark, for the introductions. It seems maybe most of you, like me, are finding our December calendar quite a bit less cluttered than it typically would be. So happy to offer a little entertainment this evening. And with apologies to the rules writing agencies, the grading rules folks that provide the values for timber for the tasteless title that we used in our advertising. This is the real title of the presentation. Looking at developing design values for two species, happen to be yellow poplar and red pine. This presentation is really about the methodology, of course, not those two species in particular. And we will do that using some parts of TFEC 3 and ASTM D245. So TFEC 3, of course, is referring to our guide to structural evaluation of existing timber structures that we issued in the TFEC last January 2019. And if you haven't dug into this, I really recommend you do so. It is an important document and a valuable document, and it plays a part of most every job I do. Of course, I'm involved in a lot of evaluation of existing warehouses and barns and so forth, but there's a lot of just good information about wood and timber design in there. So it's an important document. Dig into it. And we'll put it to good use here in two case studies, we're calling them this evening. First, we'll take a look at developing design values for yellow poplar, and that was something that got called into us as a question, and it's a species that you can't find in the National Design Specification Supplement in Table 4D for timber. So you need some way to get some values for design. This is one way to do it. Now, the other case study we've got is looking at the capacity of an existing timber frame structure that they wanted to add more load to. It happened to be red pine, although we didn't know that when the project started. So we'll be using some different parts of TFEC 3, I'll call it, in that presentation. In the first case that Dick will present, we'll be looking at yellow poplar as basically new timber, generic, not yet in use, coming from the mill. We'll leave open the possibility that it could have seasoning. It's not necessarily green, so we'll examine that. Then in the second case study, we'll talk about species ID and grading in situ, and then determining design values from there. So for those of you that are not real familiar with TFEC 3 yet and using D245, let me just set the stage for a minute and provide some structure to our presentation this evening, and then we'll get into the real detail. So D245 is a standard developed by the Wood Committee at ASTM and provides a means for developing design stresses for visually graded timber. And it's the basis for what you see in the NDS supplement. In fact, it's kind of behind the scenes there. Why we want to use it ourselves is that it, first of all, provides a code recognized way of getting design values for some species like yellow poplar that you can't get in the supplement. So it is a tool for that purpose. Secondly, it allows you to pull out individual species from a species combination. In the supplement, you find most of your various species of wood are grouped together, clumped together. And just so, for example, all the maples are lumped in mixed maple. Well, there's hard maple and soft maple, and hard maple's better. So if you know you've got hard maple, this is a way to develop design values that are a little better than what you would find in the supplement. And then finally, the method of TFEC 3 and D245 gives us a way of taking advantage of the really good quality timber that's often found in these older buildings. So we can get values that are better than Select Structural. So how does all this get going? Well, it starts by having strength values, and the strength values are derived using standard testing methods. And so ASTM D143 is the official test methodology for getting those strength values. This kind of sits there behind the scenes, but it's the basis for doing a whole bunch of testing on a bunch of different species and developing sufficient number of tests for each species that you are able to get some statistical data. And wood is a statistical material. You know, no two pieces test out quite the same. So fortunately, all that test information has been compiled and reported for us in D245. So for any given species, you can find the average strength and the standard deviation of that strength value for all of the design mechanical characteristics we're interested in, like, you know, breaking, modulus of rupture, shear strength, compression parallel, and so forth. So with D245, then you go to D245, and that basically is your operating instructions. It tells you how to take that strength data and turn it into design values. So the rules of that game are, they're kind of messy the way they're presented in D245, my opinion, but it is basically a simple process. And it's these 5 steps. You go to D245, you get the strength data for the particular species you're interested in. Maybe it's basswood. With your average and your standard deviation, you're able to calculate the 5th percentile exclusion limit, which is kind of that lower bound of strengths that were found in testing. And that's what we use to develop our design values. From there, you apply an adjustment factor to adjust normal load duration and get some safety factor in there. Step 4, we apply strength ratios to account for grade characteristics like knots and slope of grain. And then finally, if there are other modification factors that apply, we can use those if it's for wet service conditions or size factors and so forth. So that's the framework of using D245. And now Dick can take us into some of that real detail and show you all how that can be put to use. So Dick, I'll let you share your screen and take it from there.
Okay, thanks, Tom. Can you see my screen, Tom?
Yes, I can. Thanks.
Okay, good. I assume everyone else can then. So, yeah, ASTM D245, pretty compelling reading. Do it during daylight. So, but it is important that you, if you're going to follow this process, that you understand what's in 245. And as an introduction to that, I would go back or encourage you to look at Technical Bulletin, the Engineering Council's Technical Bulletin 11, and you can find that on the Guild website. So my motivation for getting involved in this process was several years ago, I was called upon to evaluate timbers on a barn, or actually barn timbers. It was no longer a barn, it had been disassembled. A client wanted to move it from Indiana to Colorado and put it up as an event center, a wedding barn. So we're looking at somewhere between 100 and 125 pieces of timber. And I read Tom's bulletin, Technical Bulletin 11, and I saw Tom's presentation on this method he developed when he presented at the latest Mount Hood conference. That was like 3 or 4 years ago, and concluded it's a detailed process. It's not real complicated to do one stick, but if you're going to do 120 of them, you're going to need some automated method for organizing it. So that got me involved. So here's what you need as input. You need to know the geographic source of your material. Is it from US and Canada? That's one set of data that you can get out of D245, or the wood handbook. If the numbers you're looking for are not in 245, take a look at the wood handbook. There are additional numbers in there. There's also numbers in the wood handbook for material from outside the United States and Canada. So if you want some exotic hardwoods from South America, for instance, then that data might be available to you as well. So identify your source. From the source, identify your species. And Tom will talk more about species identification when we turn it back over to him. Cross-section dimensions are critical. Knot sizes, the permitted knot sizes and the strength ratios associated with them depend upon the cross-section size. And then you got to measure knots, the wide, narrow face knots, wide face knots on the edge, wide face knots on the center, or a knot somewhere between the edge and the center of the wide face. And then there are grading rules for making adjustments on how big those can be. You got to measure slope of grain, and you need to know your in-service. Well, you don't need to, but it's helpful to know your in-service moisture content. If you have an in-situ situation, then you can really bump up your design values by knowing the moisture content. Otherwise, you're stuck with using the values for green material. So you're at fiber saturation point. All right, let me see if I can get this turned on. Okay, so the outline, to repeat what Tom talked about, you collect your small clear test data from either D245 or, in addition to that, the Wood Handbook. Calculate your exclusion limit. Apply the adjustment factors. They account for the factor of safety, a factor of safety that gets you even farther below the 5% exclusion limit, as well as accounting for duration of load during testing. So that 1.6 factor that we use for 10-minute load duration, wind, for instance, that's taken out of the test data in order to get the long-term load data. Apply your strength ratios, the critical one for either knots or slope of grain, and then there's a handful of other adjustments, and we'll go through those in turn. So again, here's your sources for the small clear test data. Focus on the average value and the standard deviation. Those are the two numbers that you need for each of the material properties. Bending, modulus of rupture is bending, modulus of elasticity, compression parallel, compression perpendicular, shear. Calculate your 5% exclusion limit. We assume a Gaussian distribution. The mean value mu is reduced by 1.645 standard deviations. Sigma is your standard deviation. And that gets you down to that little shaded area with the red hatches that has an area of 0.05. And for a normal distribution, the area under that bell curve is 1. So you're at the 5% exclusion limit. Apply the adjustment factors. These are in D245 table 8. And for softwoods, for bending, we divide by 2.1. Divide our 5% exclusion value by 2.1. For hardwoods, divide by 2.3 for bending. For modulus of elasticity in bending, we divide by 0.94, which actually increases the value. And that's due to some vagaries, not vagaries, but some peculiar characteristics of the test procedures, the small clear specimen span to depth ratio versus a typical bending member. And then I'll let you can look at the rest of these when you are reading D245. Apply the strength ratios for knots. Table 2 in D245 has strength ratios. For instance, if I have if I'm looking at knots on the narrow face of a bending member, I've got a 4-inch wide member and a 1-inch knot. My strength ratio is 78. And what that means is 0.78 is a multiplier that I use on my design value. Or I've lost 22%. The knot has reduced my capacity by 78%. These tables are a nuisance to try to use in any automated fashion. But fortunately, the annex as equations that give you roughly the same values. So 10.1.1 is knots on the narrow face, and the equation we use there is shown in blue there for a 1-inch knot on a 4-inch wide face. I calculated 78.1, so essentially the same number. The strength ratios for slope of grain are listed in table 1. And for a select structural beam and stringer, the greatest slope of grain you can have, or the limiting slope of grain, is 1 in 14. The strength ratio for bending is 74, and for compression parallel to grain is 87. So very similar to the knot size number for select structural. Strength ratio for shear. There's a lot of reading on this. I'm not going to let you or give you the time to read it, but the point is, just look at the first line. Strength ratio of 50% is used for shear for shakes, checks, splits, and also accounting for some of the nuances of the test procedure versus in-service performance. Other adjustments, the modulus of elasticity is modified by a quality factor. What that means is if you've got a timber with a relatively low strength ratio for bending due to high slope of grain or large knots, the stiffness is actually lower than for a better quality material or a better quality stick of the same material. So you have a reduction in the modulus. Tension parallel to grain, it is always 55%. That design value is 55% of the bending value. And the reason there is when you apply tension to a member, you're stressing the entire cross-section, exposing more strength-reducing characteristics to stress and potential failure than you would be in a bending situation. Specific gravity classes for close and dense grain allow you to increase your design value for instance, dense Douglas fir or dense southern pine. So those are given to you in table 6, and those can be significant too. So these are the quality factors for modulus, just table 5. These are the adjustment factors for close and dense grain. And I'm going to skip over these anymore. I'm not going to spend any time on it. Incidentally, I will point out they apply only for Douglas fir and for southern yellow pine. Don't try to apply them to a dense true fir or eastern white pine or any other material like that. They depend upon both ring count, number of rings per inch, and the percent of late wood. So you can't just count rings. You also have to evaluate how much late wood you have in the cross section. Okay, here's a big one. Now, if you're working with seasoned material, then you're permitted to increase the allowable properties from the green values based upon the moisture content. So for bending, for instance, you can take a 25% increase in your bending design value if your timber or your stick of lumber is at 19% moisture. You can increase it by 35% if you're down to 15%. So we've got two numbers here, or two data points, 25% at 19, 15% at 35. I can draw a straight line through those and write an equation of that straight line and then evaluate, well, what if I'm at 12% or at 16.5%? Then basically the idea is I can come up with a C sub M, if you will, for any moisture content. So moving on with that. That should be exciting. So, okay. That's one of the take-homes on the take-home messages for this presentation. So that straight line for bending has a slope of 2.5. That is, for every 1% change in moisture content, I get a 2.5% increase in my design value. Likewise for tension, for shear, 1 1/4, and so on. So that column under that rate column is taken from table 10 in 245. We've applied a lower limit of 10%. If the equilibrium moisture content is 10% or lower, that's the shelf or the bottom at which we're going to make these adjustments. Because if you go any drier than that, you really don't get any additional increase. And that's based on research that Ron Anthony has done. Incidentally, the lumber moisture content, in green condition, we assume fiber saturation point is 29%. For timber, we're going to make similar adjustments, although D245 says you don't make adjustments and then it contradicts itself later. We're going to make adjustments. We're going to do 4% change in the bending strength for every 1% change in moisture content, down to an equilibrium moisture content of 10. And then all of these numbers are based upon Ron Anthony's research. So other adjustments for compression parallel and for E, section 7 of the standard talks about that. If you translate the black text into blue, it says timber strength increases as moisture content decreases. Okay, that's the good news, and we can exploit that. So the other adjustments are, the size factor is C sub F is equal to 2 divided by D. D is the depth of the stick you're working with, to the 1/9 power. The 2 is there because in the D143 test procedure, you're breaking a 2x2 cross-section stick. And if you're using a 12-inch stick, or 12-inch deep stick, obviously you've got a greater dispersion of knots, greater opportunity to account for that. Always include that. You always want to make that adjustment, or you're going to be over-predicting your strength. You're
That's
going to
for
be on
bending only,
for
right?
bending, for bending, right? Or you're going to be on the wrong side. Incising, load duration, temperature, all of these things that we normally do when we do design, then you obviously make those same adjustments as they're appropriate. So a summary, in order to calculate F sub B, your reference design value for bending, start with the modulus of rupture, reduce that by 1.645 standard deviations, divide that by the adjustment factor of 2.1 for softwood, 2.3 for hardwood, multiply by the strength ratio, controlling strength ratio, either knots or slope of grain. C sub F is the size factor, and then C sub M is your moisture adjustment. And you're done. So 2 minutes, and you've got that number knocked out. If you only want bending. If you want all the others, there's 5 other values that you can calculate. They use roughly the same procedure. And then if you got 120 sticks, you need a way to automate this. So let's look at the sample design values for yellow poplar. And why yellow poplar? Well, because Jim Rogers needed the numbers. He sent out a broadcast email some time ago to the Engineering Council, and he got some feedback on it. And one suggestion was just use eastern white pine. Well, you're going to pay a penalty if you do that, because yellow poplar is substantially better than you're going to get out of eastern white pine. So here's what I've done. I'm going to assume that I've got a 6x12 beam and stringer or a 12x12 post and timber. I'll use the NELMA limits for knot size and slope of grain, Northeast Lumber Manufacturers Association. And I'll assume a moisture content of 12%. we assume the fiber saturation point for timbers, again, based on Ron Anthony's research, as 22%, not as high as 29. The testing work that was done on timbers to actually break full-size timbers to get the data that we use in Table 4D averaged around 22%. So here are the knot sizes and slope of grain limits based on the NELMA standard. For a select structural beam and stringer, the edge of the wide face can have a knot that's 2 1/8. The center of the wide face, 3 1/8. Slope of grain, 1 in 14. Post and timbers, 2 3/8 anywhere on the wide face. Slope of grain, 1 on 12. Let me call your attention to a number 2 post and timber. Our timber is 12 inches deep, nominally. I can have a 6-inch knot all the way through that timber. 6 inches across, all the way through, and still call that a number 2. I'll leave that for you to decide if that's how if you want to use that stick. Okay, so here are the calculations. The modulus of rupture for yellow poplar is 5950. Standard deviation is 952. Adjustment factor is a hardwood, 2.3. My size factor is 0.819, so let's call that 0.82. You'd be 18% over unconservative if you forgot to use the size factor. The moisture content adjustment is 1.4, so I got a 40% bump in my moisture due to moisture content. On the right side there, my strength ratios for the 4 quantities, I have 3 knots in slope of grain. The edge knot at 2 1/8 is controlling 0.694. Cram all those into my equation, and I calculate a bending value of 1500 psi. If I overlook the moisture content adjustment, assuming that I've got green timber here, then take that out and I'm at 1100 psi for the bending value. Excuse me. Okay, so the computational tool I put together based on Tom's work and his inspiration looks like this. It's a big spreadsheet. The blue cells are your input. The pink cells are interim computations, if you will. And then down at the bottom, the tan is the output, the final values. And let's see, so this particular sheet is for a 12 by 12 cross section. It's classified as a timber since it's bigger than 5.5 or larger, or 5 by 5 or larger. I picked US and Canada as a source. Incidentally, notice the N next to the Canada. In the pull down menu, any material that comes from Canada has that N next to it, meaning north. That's the code that's used in the NDS supplement, so I duplicated that. So I picked yellow poplar. The strength data from D245 is listed here, or all the characteristic data. Calculated values follow, and then down at the bottom are my design values. Again, this is my post and timber 12 by 12, and in this case, I've got 6-inch knots everywhere, and I've got a slope of grain of 1 on 6. The controlling strength ratio for bending is 0.253, governed by my wide face edge knot. Again, for shear, it's always going to be 0.5. My compression parallel to grain value, 0.52. Okay, moving on. The scope and limitations of this worksheet. It's based upon data in D245 and the Wood Handbook, based on green, small clear specimens. The D245 strength ratios and most other adjustments are used directly. Not included are the adjustments for close and dense grain, because we don't always have southern pine or Douglas fir. And if you're doing an in situ study, you're not going to be looking at end grain very often. You don't see the ends of the timbers very much. The in-grade program for lumber, though, this objective here is not to duplicate the NDS supplement, is to come up with values that are not supported by the NDS, or that are not in the NDS supplement. In a lot of cases, the numbers are very close. If you want to make a comparison, fine. But the point here is, it's to, as Tom pointed out, the real value is if you know the actual knot size and it's smaller than that 2 1/8 for a 6x12 beam and stringer, you can exploit that. If you've got a material that's not the weakest in the species combination, you can exploit that. Okay. So the yellow poplar design values at a 12% moisture content look like this. And they look pretty good. If you compare those to D2 or the table 4D in the supplement, you're going to say that, oh, that's a pretty robust material. And keep in mind, I got a 40% increase there on my bending values to account for the moisture content. So let me pause for a moment. I want to drag this over. Okay, am I still sharing that screen? Can you see the spreadsheet?
Yes.
Okay, here's the spreadsheet. In this case, I've got the 6x12 timber with the knots and slope of grain corresponding to select structural beam and stringer. Let me change my moisture content to 22%, and there's the adjusted design values. So it's that easy. All right, spend another few minutes here. Strength ratios for slope of grain, I've got them in based on an integer format. That's not an they're not in equation form. For moisture adjustment, bending, tension, shear, compression, perp, compression parallel, E and E min, all potentially different for timber and for lumber. Fiber saturation point for timber is 22. For lumber, it's at 29%. So if you don't have this spreadsheet, I know some of you do, but if you do not have it and you would like a copy of it for your professional use, your obligation is to understand how to use it, read D245, accept the disclaimer that comes up when this thing opens, and add your name to the chat box indicating that you want a copy of the spreadsheet. If your name's in the chat box, Mark will share it with me and I will send you a copy of the spreadsheet.
To clarify that, Dick, if you put your name in the chat box, put down that you want a copy of the spreadsheet separately, because we're asking people to put their name and their phone numbers in the chat box for their AIA credits.
Right. Yeah. Yep. The point, say spreadsheet, that'll be enough, and I'll send it to you. What I don't want to do is put it on the Guild website and have somebody use it without any understanding of how this stuff works, because there's a potential to do things incorrectly. So I'm going to stop there and turn it back over to Tom so he can proceed.
Thank you, Dick. All right, well, let me jump down here just a little bit.
Oh, can I jump in for just a second? If we have time at the end, I'd be glad to go through a live demo of the spreadsheet. If there's interest in looking at other design values, other materials, or
come on here.
we could play around with knot size and see how that affects things.
Great idea.
Are you doing questions at the end or throughout?
Let's go ahead, David, and jump in since Tom hasn't really started yet.
Okay, sorry. Just curious, it was fantastic. Just curious, where do you get the standard deviations? Is that because you've done testing, or is that listed somewhere?
That's also listed in D245, or also in the Wood Handbook. So both the mean values and the standard deviations for the green small clear specimens. So it's a pretty good statistical basis. And in fact, that 1.645 number, that multiplier is used in statistics if you have an infinitely large sample and assuming that you've got a perfect bell curve. But that's what the standards D245 says to use that, so that's what we're doing.
Let me add a comment there, Dick, that the standard deviation is not given in the Wood Handbook. So David, if you do happen to use values from the Wood Handbook for some reason, like you're looking at black locust, read Technical Bulletin 11, and it will give you some guidance on the appropriate standard deviation to assume for the various strength values. They happen to be very consistent throughout. They're basically assigned for most species. So
that's a good point. For instance, specific gravity, the standard deviation on specific gravity is 10% of the mean. So if you've got a mean of 0.4 for yellow poplar, the standard deviation is 0.04.
For that property.
Okay, I'll stop now.
Okay. Yeah, if you do have questions, folks, you can use the chat box as well. Start typing some questions in, and then when I get done here, we'll read through them and see what all we can answer. So thanks. Well, let me turn now to more of a story, a little easier on the brain, perhaps. Tell you about a project I got involved in earlier this year, back last winter when snow was still on the ground. I was asked to come up to Traverse City, which happens to be a favorite destination of mine anyway for skiing. And this is one of the anchor buildings downtown in the historic Main Street area, the Nehil building, named after the two gentlemen that were the developers. Traverse City, yeah, is a booming little place, and the owner was the developer and was in the process of renovating that 140-something-year-old building to add more condominiums and more office space. And so as part of their work, they wanted to add another story to the building in certain areas. And they were interested to know whether the posts were strong enough to handle the extra load. In particular, that was one of their concerns. I actually got the reference from Rick Shoemaker. Rick's a timber framer up in Traverse, and he is with Strong Timbers. And so they talked to him, and Rick's in fact been through our timber grading training workshop, and he knows the stuff, but the engineer working on that project was not comfortable with the idea he was going to be consulting with a carpenter on values like that. So Rick told him to get a hold of me, and so I got involved thinking I could maybe add a little something extra as well. So Traverse City is kind of a Four Seasons playground these days, a vacation spot, great retirement place. It did not start out that way. It started out like most of our Lake Michigan coastal towns and cities. It was a lumber town, shipping lumber out of Michigan to ports around the Great Lakes. And that picture that you see at the top is about what Traverse City looked like in 1870, not particularly glamorous. The map in the lower half there shows you Traverse City in the northwest part of the lower peninsula of Michigan. It's kind of a neat spot in that it's located at the south end of Grand Traverse Bay, which is a 30-mile long bay. So it's really well protected from the big storms that come across the lake. But it's also at the mouth of the Boardman River. And so it was a perfect spot for shipping logs out of the swamps and woods during winter and spring, milling them at the mouth of the river, and then sending them off around the lakes. And so that is where these two gentlemen, Hannah and Lay, made a good bit of their money. They were Chicago businessmen that invested in the lumber business, and this is their mill at the mouth of the Boardman. They became real lumber barons, and downtown doesn't look like this anymore, I can tell you. Well, people were so good at cutting down trees in Michigan that in about 20 years, all of a sudden they started to notice that they were running out of trees, and the whole lumbering business was starting to move west. So the unlimited resource suddenly became very limited, and these two guys decided they'd better diversify. So they got into retail and real estate and various things, and one of their ventures was to build this building, the Hannah Lay building, about 1883. And it was called the Big Store. It was the biggest commercial building north of Grand Rapids. And so that means basically the northern half of the lower, and I would think the UP as well, eh, Joe, if you're on the call. So back to the story. They wanted to know whether the posts were strong enough. And of course, my questions to them were, well, what kind of wood have you got? And what kind of service stresses are you talking about here? You know, what sort of strength do you need? Well, they did not know their species, and of course they didn't know the grade. But the crazy thing is they had not even run the loads, or they really hadn't developed any kind of a picture of how strong the wood needed to be to do the job for them. And that's backwards. You know, before you waste any time going out worrying about your species and your grade, you ought to at least know whether you have something that's either a no-brainer or unachievable or somewhere in the middle. So, you know, if this guy had calculated that he needed 3,000 PSI F sub C, in other words, axial compressive stress, you know, you could have told him, well, you don't need me. It's not going to happen. You can't get there. And similarly, if the loads were light, if he only needed 300 PSI, there's no reason to worry about what kind of grade or species you have, because everything's going to work. If you're in the middle there, if you're in that gray zone, you need 1,000 to 2,000, something like that. Well, then, yeah, it's worth investigating. So, step one, we got to find out what kind of wood we got. And so I gave them some guidelines on how to go about collecting samples in a way that wouldn't harm the timber, wouldn't make the structure ugly with scars. And so here's a picture of where they picked up their drop ceiling in an area and broke off a corner of the post. And so they did this in various locations and sent me samples through the mail so we could get a jump on this thing. And I looked at the samples and did my own identification, and I determined they were all red pine. So ducking off into the species ID world for just a moment, the question is, how did I know that, right? So here's a little bit of a taste teaser, shall we say, on what's going on when you're looking at wood identification. One, of course, I looked at the color and the unevenness of the grain, which, you know, red pine is something like hemlock. It's what they call moderately uneven. You can distinctly see the dark wood, the late wood, as different from the early wood. So it's easy to count the growth rings because you've got a nice dark line at every summer growth period. So hemlock and red pine look similar in that, but red pine has a very sharp odor that hemlock does not have. So it's definitely kind of a turpentine resinous odor that distinguishes it. If you pulled out your little 10x handheld magnifier and looked at the end grain on the red pine, you would see resin canals, little dots, you know, where the resin resides, you might say. hemlock does not have those, and maybe that's why it doesn't have much smell either. But beyond the gross characteristics, we can also dig into some of the really microscopic anatomical features of the wood to make a more definitive determination of the species. And so just to throw a little terminology at you, the things that red pine has that are definitive are window-like crossfield pitting and dentate ray tracheids. And, you know, those are the words, the unavoidable terminology that's involved in getting into wood anatomy. But to give you the picture instead, red pine on the left here and hemlock on the right. The caption there shows you the window-like crossfield pits, kind of like a car window, a little bit of a parallelogram. And then bordering the rays are these gnarly looking cells that are called the dentate ray tracheids. So these two slices are like thin slices taken right down the length of a ray along the radial section. And that picture on the right is all you would really need in this case to make an absolutely definitive assessment that this was red pine. Those characteristics are unique to red pine. So it's one of the species where you can actually nail it right down to the individual species rather than just the genus. So if you're interested in some of this stuff, why don't you holler at Mark and, you know, let him know that you're interested in another wood identification workshop, and we'll see if we can get one pulled together. I enjoy teaching it. It's a lot of fun and so fascinating to see what's going on inside those trees. Well, we had the species now, red pine. We now need the grade. And this was the scene where I was going to be going in and trying to grade the posts. It's not ideal in that the posts were not fully exposed, but I could see two sides or 2.5 sides basically where the partitions weren't covering up the grain. And so I got in there and gave it the visual review and determined that the grade was completely awesome in this building. It was the best red pine I've ever seen anywhere. And I've seen some good stuff, but this was incredible. Those guys, those lumber barons picked out the best of the lot for their own building. The grain was so straight that there was nothing to measure. I mean, call it 1/16 or 1/18, anything would be reasonable. It was dead straight. I could not find a knot. It was just clear material, really wonderful stuff. Because I could not see all sides, you know, every surface of these timbers, I looked around the building where there were other posts that were exposed on all 4 sides, so I could get a better sense of the consistency of the quality in this building, so I would know whether to be concerned about what I couldn't see. Really about the same thing on all levels throughout the building. I had to walk around all 4 sides of these posts to even try to find a knot. There were very few knots. It was the clearest red pine I've ever seen. If I did find knots, they were maybe 1 inch, 1.5 inch diameter at the surface. And this is box heart timber. So if you read Dick Schmidt's article in Timber Framing here, just 1 issue back, I think, you'll know that the effective size of a knot like that is much smaller. The displaced area due to that knot is only roughly 1/3 of what you measure as a size at the surface. So these were, for practical purposes, knots that would be called 1/2 inch knots or even smaller when you're looking at the grading rules. So clearly much better than Select Structural. So with that information, it was time to get my reference design values. Red pine is in the supplement. I mean, I could go to the supplement and take those values straight out there. For Select Structural, I would be safe. But, you know, I'm in the habit of using D245, so I do it anyway, as a matter of fact. And knowing that I had something that was better than Select Structural, it was going to make sense here. I learned something about red pine that I had never really considered before in the process. I developed my design stresses. I think it must have been 2 different sit downs. And the second time I went to take a look at my calcs and compare what was in the book. I didn't have the supplement with me. I just had the NELMA grading rules, and NELMA has the design values included at the back of the grading rules book. So I went there and I noticed that the numbers were not the same as the numbers I had jotted down from the NDS supplement. They were higher by 10–15%. So I had never really considered the fact that the values in table 4D, if you look in the right-hand column, you'll notice it tells you that they are per the NLGA, the Canadian Lumber Grading Agency. Well, you know that the Canadian values for Doug fir are better than the Doug fir South. I guess I kind of thought maybe red pine was the same way, so they just gave us the good stuff. Well, no, NELMA, the values that they list and give you for red pine are based on a different test set. The samples were sourced in the USA. Somehow they're better, they're stronger. Those values are given in D245 in their table 2. Table 3 is for Canada, woods grown in Canada. And if you run the numbers, you'll see that the values given in the NDS supplement can be derived by using the table 3 values. So it's clearly, it's a Canadian data set. I don't know why we don't see both in the supplement, just like we see both Canadian and then Southern Doug fir. Why wouldn't we see kind of a Northern and a Southern red pine? But we don't. I have not been able to get an answer from AWC or anybody about why we don't, but now you know. And if you feel confident that you have, you know, old line red pine from the US, then consider using those US values. So here's how it all compares. If I went to table 4D and took values right from the table, I would get a axial compression parallel to grain, 775 PSI, and the E would be 1100. NELMA for Select Structural gives you 875 and 1400 for the Modulus. What I came to these guys in Traverse City with is I said, why don't you look at 950? And I based that on the, call it super select value. That is the small knot size, the straight grain. So I developed this value. I did not take any big bump for moisture content, and I could have, because that timber was bone dry. I mean, easily 12% would have been fine. So I just took the 10% increase for dry service conditions, but otherwise treated it like a green timber. And I did that just to kind of feel out the client, essentially, the engineer. As it turned out, they were satisfied with what I gave them, and I didn't have to go really out on a limb suggesting that we use a moisture adjustment, but I would have been comfortable doing so. I think it's reasonable because D245 suggests that you not do it, because if you take a green timber and grade it and give it the design values, some bad things might happen when it dries. You know, it might develop crazy checks that split it in half, full length. So, you know, they've kind of got a worst case scenario in mind, and they want to make sure nobody gets hurt. But I wasn't looking at green timber. I was looking at stuff that was 140 years old, completely seasoned, and I could tell whether any defects had developed. And they hadn't. There were no defects. I mean, the checks were small, if any. So I would have been very comfortable using Dick's calculator, for instance, setting the moisture content at 12%, in which case I could have had a compression parallel of 1500. They're really good. We didn't need to do it that time, but in any case, knowing that that's an option, I think is helpful for all of us. By the way, Dick's spreadsheet has both the Canadian and the US strength data for red pine. So you make that selection, you know, it's your choice on which strength information you want to use to start your calcs. So we can apply those moisture effects if we feel comfortable with the condition of the stick, that it hasn't developed defects. But you want to be looking at the stick, not just kind of arm waving. And so that's an in situ grading sort of decision. I think it'd be great if we did a little more work in TFEC to show seasoning effects for compression, for shear, and maybe bump up the ones that we're using for bending so far as well. So we'll wrap up the comments here, I guess, first of all, just to advise all of you, consider using TFEC 3 and D245 whenever you're evaluating existing timber. It's fast, it's easy, you know. It's really, the equations look a little daunting at first glance, but it's a 1-minute calc. So great, use Dick's calculator, but know what you're doing. It's not gonna take care of any ignorance on your end. You need to be the one with the intelligence using the tool, and use judgment in applying the moisture C sub M effect, right? And I recommend to all of you to take the timber grading training workshop if you haven't yet. Obviously, we didn't offer it this year, but we hope to in upcoming years. So again, if you're interested in that sort of thing, be getting in touch with Mark. Let him know that there is the demand. So with that, I think we can take a look at questions, and let me stop sharing here. Now I can see the chat. And Dick, have you had a chance to pick out any questions in particular?
I've been sharing a couple. Yeah. One question was, what was the magnification that you used in your micrograph? And my response was, I use a 200 lens, and my eyes aren't as good as yours, or not as well trained. So I suspect maybe 100 is sufficient for you. So I'll let you.
Yeah, that view was at a 200 power. That's a good power for looking at the rays and the ray cells. So that's a good answer, Dick.
Okay.
200. So you need an ocular that's 10 power, and then the objective is 20 power on your scope.
So yeah, I've been related to the whole group. I haven't seen any other questions other than that Scott Ratterman wants another wood identification workshop.
Hey, okay
So
then.
that's for you, Mark.
Thanks to Tom and Dick on the presentation. I don't know if I can pose a question.
Yes.
Can you hear me?
Yeah, go ahead.
I guess I'd like to get your thoughts on looking at historic timbers and maybe how we might extend this approach to looking at connections, particularly tension splices, and looking at kind of the higher quality at local joinery, and maybe paying attention to that 50% increase for shear value.
Yeah, the 50% strength ratio that's applied automatically to shear, Sergio, is kind of a goofy feature. It relates to bending capacity, as a matter of fact. It's not really an assessment of shear strength, particularly not shear strength perpendicular to grain. It's parallel to grain. So 50% was considered the worst case scenario, where a timber splits from end to end, and that's the impact it would have on a split timber's ability to support load in bend. So it's not really a good factor when you're talking about bearing connections, direct shear, block shear at connections. I have been researching this question for a couple of years now, trying to find the source and all of the thinking that goes into that 0.5 strength ratio for shear, because it doesn't seem appropriate that it would be applied automatically across the board, regardless of whether splits or shakes or checks are present. So if you have an area in a connection with no checks or splits, do you really need a strength ratio? just my personal thinking so far on that is that maybe you don't need a strength ratio, but maybe you need an increased factor of safety because shear is a brittle failure mechanism. I don't think the factor of safety needs to be as big, but I've been working on this with Ron Anthony for a while, and we're trying to dig back through all of the literature going back 100 years and see if we can't trace the story. It's one of the more confused aspects of design values in wood, in timber. So don't have the answer exactly for you there, Sergio, but I think there's my guess is that allowing some increase in shear for block shear conditions is not unreasonable. We'll hope we can make that official sometime in the near future as
Thanks,
a recommendation.
And sorry to put you on the spot too.
No, that's great. Thank you for the question. Was that the full answer that you were looking for?
I'd love to see some joint busting.
Well, yeah, you know, statistics, you do a lot of joint busting.
What about the determining moisture content? How do you do that? Do you use like a moisture meter or a particular kind of moisture meter?
I've got one right here, Raul. So this is a Delmhorst. Let me,
Bring that.
Here we go.
Yeah, okay,
so we've
it's a
got
thin
pins on
pipe.
the end of this hammer thing, pounded
Yeah.
into the timber, and then you calibrate this, set it for the particular species that you're using, and it'll give you a value. Ignore anything to the right of the decimal point. If it says 12.3, it's not 12.3, it's somewhere around 12. That's going to be a better approach. Get moisture content down below the surface. They have moisture meters that'll just measure surface moisture content. That's not going to give you a good value. And even this guy, this impact pin hammer thing, isn't going to get all the way in, but it's better than being right on the surface. And it's a Delmhorst.
Okay, I saw some radio frequency kind that are supposed to read down about 3/4 of an inch, but it looks like those pins could go deeper than 3/4 of an inch.
Yeah, you can get pretty long pins. It's sometimes difficult to get them back out. So you might end up losing them.
Do you have a brand that you're using you recommend there, Dick?
This is a Delmhorst, and that's a pretty high quality unit. It's going to cost a couple $100.
Hey, Dick, Ron Anthony, you mind if I jump in for a second?
Go right ahead, Ron. Everything I know about moisture content comes from you anyway.
So Dick is correct in showing you that moisture meter, but I'm going to suggest don't cheat. All right. Everybody knows the moisture content, even in situ, changes throughout the course of the year. And so really from a design standpoint or a long-term strength standpoint, you're interested in the equilibrium moisture content. So I've known people that have said, I'm going to go out in the driest time of the year and take my moisture content reading and use that. That would be incorrect. You want to use the average moisture content over the course of the year, basically the equilibrium moisture content. So taking that reading in the building will give you a sense of what that is, but there's also a Forest Products Laboratory publication on equilibrium moisture content that you can use to get that value. So don't fool yourself into thinking, hey, I'm in Miami and I happen to get 7%. This is great. That's not the way to do it. You need to use that equilibrium moisture content value.
Other questions?
Yeah, we had a question in the chat wondering whether or not the spreadsheet output has been compared to the NDS and the CSA 086 values.
I've compared it in 4 or 5 different cases to timber design values, and in some cases it's right on the money. In others, it may be 10 or 20% different depending upon exactly what you're looking at. I'll mention that the grading rules from NELMA and WWPA and others are a little bit different, or particular for knots, are a little bit different than in D245. For instance, the NELMA uses the WWPA, Western Wood Products Association rules, and they no longer look at, or they don't standardize, they evaluate an edge knot or a narrow face knot based upon the same displacement as on the wide face, which if you read that article we wrote in Timber Framing about the displacement method, I think you'll understand that. But basically, that's different from D245, in which narrow face knots, wide face edge knots, and wide face center knots are all treated separately and differently. So it's close. The numbers are close to the NDS supplement, but you have to pick the correct value, your material as well. You got to pick the lowest value in the species combination.
Good. I hope that was helpful. Just to clarify a couple of things, because we're getting lots of interest apparently in wood ID seminars. The TFEC has put on a variety of courses, including a species ID level 1 and a species ID level 2, and there's 2 different courses there, and I'll get Tom to talk to those in a minute. But we've also put on a grading course, and this follows up directly with Dick's article in the recent Timber Framing Journal on knot sizes and assessing knot sizes through what do you call it, proper grading and evaluation. So there's 3 separate courses there, plus what do you call it, all the other stuff that we've been talking about this evening. So if you're interested in a grading course that's separate from the species ID, let me know. And if you're interested in a species ID course, we have 2 levels, and I'll get Tom to address those and to talk about how that whole system has gone in the past.
Oh, sure. Well, the course that we've offered, what we're calling, level 1, kind of starts at the beginning, looking at physical characteristics, color, smell, weight, then getting into a little bit of the anatomy, and using handheld magnifiers and pocket knives and so forth, but not really digging too deeply into the microscopic stuff. So level 2 is where we'll take it to the microscope, and we've done this once. We did it at the Forest Products Lab with the help of Alex Wiedenhoft there, who heads their wood ID department. So that was a great experience. They had lots of microscopes available, very helpful. That is one challenge to putting on the course, but problems are there to be solved. So level 2 is more in the microscope sort of thing, and level 1 is sort of that practical stuff that you can do easily without having a microscope.
I have a comment.
Sure, go for it.
Dick mentioned that the determinative quality of grain is the amount of light wood. And that's an unbeatable way to look at it. But there's a lot of confusion between close grain and dense grain. That is, they're taken as equivalent, but they aren't. And I was curious enough about this once in the course of doing a book review. It's in TF 52. And I took some samples of Douglas fir and I oven dried them. They were of different rings per inch. So I discovered that close grain is not dense grain. In the case of Douglas fir, there was less light wood in the close grain samples than there was in the relatively coarse grain samples. Most people are familiar with this in hardwoods, in oak, for instance, where you can see the spring wood and the summer wood very distinctly. And people have long noticed that a major proportion of late wood in oak makes it a lot stronger, up to the point where it becomes too brittle. But anyway, I think that's an important point, and I'm glad that Dick mentioned it.
Mhm.
Yeah, from a numerical perspective, close grain allows a 7% increase, whereas dense grain is 17%. But you do have to have skill as a grader to be able to look at end grain and say, yeah, that's 40%.
Yeah, well, it also may be that close grain has certain advantages functionally, and that dense grain is a measure of specific gravity only, which isn't necessarily always advantageous in proportion. Anyway, it's a little complicated.
Yeah, if Ron is still on, maybe he can address that as well.
No, I think Ken did a great job of explaining that.
Perfect. Are there any other questions before we wrap things up this evening?
One question, has anyone, have any of you looked at doing, at creating a higher grade than Select Structural for new material? Where a lot of the timber frames, particularly the Douglas fir that the timber framers are using, is well above Select Structural. And I'm just wondering if any of you have thought of using this method of quantifying that, and for material that we're already getting, and that's high quality, but like a clear grade, for example.
Well, a good question. You still need some standards as to what are the limits on the strength reducing defects, not defects, characteristics. A knot is not a defect in a stick, it's a characteristic. So, you know, if you were to choose half of the Select Structural limiting values, and, you know, for knot size and slope of grain of 1/20 instead of 1/14, you're going to get higher value, design values. But I think it's probably not in our best interest to offer those design values as a second supplement to the NDS, if you will, for the really high grade material. This is where an engineer or someone, a wood scientist or someone with the skills to do the analysis and understand what they're doing can do it on an individual basis.
Good, thank you.
So I see a question there about using the spreadsheet for South American values. I do have, I think I have IPI in there. Let me share my screen and appreciate everyone sticking with us. So I've gone to under geographic source outside the US and Canada. There's the material. Average modulus of rupture is 22,600 PSI. And if you got a 6 by 12 stick of that, satisfying the WWPA Select Structural requirements, you can use 4,000 PSI for your bending stress at 22%. 12%, 5,700. We're joking here, okay? So keep that in mind, that there's some capability to the spreadsheet that we might not want to exploit. But having shared the screen, let me go back to US and Canada. And I want to go to maple since Tom mentioned that. So if you have silver maple, the asterisk in the next to the name means this is the weakest bending. This is a species with the lowest modulus of rupture for that genus. So the modulus of rupture for silver maple is 5820. If I have sugar maple, 9420. So this is where you really get the boost if you know exactly the material you're working with rather than just the genus.
Yeah.
Just, Dick, this is really great. And thanks for the presentations, both of you. I just for certain perspective, what we've done at times in Canada is we really don't have many species listed. I think we have, and Mark, you can confirm this, I think we only have 4 species listed, or species groups, but we don't, it doesn't really break it down for us the way the NDS does. So what we've been doing is when this does happen, we'll look up in the NDS to get the species, and then we'll pick a known species in the NDS and do a ratio to the Canadian values and come up with kind of a conservative perspective. So we're not going to get an exact number, but it'll be kind of close and give us at least some comfort when we get a species that's different. So I think what you're doing is fantastic because it's so fine-tuned, and it's even way beyond, I think, our wildest dreams of where we could get with fine-tuning the strengths on these things.
That's a good point. For instance, Hemfir North. Let's see, how many species do we have in that? Well, just 2. But and then you got 2 eastern hemlock and tamarack, a couple of western cedars. So you know, your groupings are smaller. That's fortunate. They're not nearly as big as ours, which means we have generally a lower bound. That's even lower.
No, it's actually the opposite, Dick. We only have 4 groupings, period. We don't have individual species other than Doug fir hemlock. So that when I go to design in white pine number 2, we have what's called northern species, which is non-commercial junk species. And you can imagine what number 2 design values are. So when I design in northern number 2 for white pine, I call it structural butter. The piece sizes are ridiculous. But the interesting thing is that the information that I gleaned from the grading course and the subsequent follow-up in terms of this spreadsheet that Dick has put together, my understanding of the values of the material we're using for bending members in particular has changed dramatically. When I order a number 1 grade material and I can get it from certain mills, we're not getting number 1. We're getting this super structural that Tom was talking about. We're getting knot sizes that on the 10-inch or 12-inch face that are in the order of actual measured on the face, only an inch, inch and a quarter. And we're using box hard timber. So when you actually do the knot size on these things, these are 5/8 or smaller knots. Slope of grain on all the stuff we're getting that's 12 inches and wider is always way higher than 1 in 16. It's like Tom said, it's pin straight. And so the material that when I'm designing stuff, when we have a huge factor for piece size, when you get above 12 inches, we start taking a hit hard. But when I look at the strength of the material we've got using this calculator of yours, Dick, on a 12-inch white pine, and we measure the knot sizes and the slope of grain and the moisture content, we're way above select. So I've been over designing big pieces like purlins, summer beams, those type of things, principal purlins. I've been over designing them for decades. And it's amazing how much of a strength you can get from this. I mean, Tom, your one calculation showed a 40% increase because the moisture content was below 22%. This is a huge tool for consulting engineers and practicing timber frame engineers like myself. It makes a huge difference in terms of the way I approach materials. You talk to timber framers who work with ancient material, they're saying all the time, well, geez, you know, the purlins in this 20-foot bay are only 8x10s or 8x8s. And you're like, that doesn't make sense. Well, the problem is that what I thought made sense actually doesn't make sense in the real world. And it's a huge change in the way that I approach wood.
Well, the purlins usually don't make sense anyway, Mark, but another story.
So Mark, you're grading that up. So you're because you have control. It's in your shop.
Yeah.
You're like creating a higher grade that you're designing for, essentially.
To a degree, I've stopped ordering #2 material because I just don't like the look of it. But the qualifiers that I had put in internally on our material bumped it up almost to #1 grade anyway. The only thing that was determining the grade was the knot size. And when we use box tart timbers in square sections, 6x6, 8x8, those types of things, the knot size tends to be large. Versus if I go for a beam and stringer grade, I'm looking at a 6x12 or an 8x12. Knot size, especially those timbers, tend to be long. Anything over 16 feet, the knot size dramatically drops. We're getting sometimes clear 8x12s that are 24 feet long, perfectly straight grain. So why am I designing them? Why am I designing them at #1 or #2? These things are gargantuan strength compared to what the 086 Canadian values allow. And back to David's point about using this, I've done exactly what he's done. Looked in the NDS and looked up strength values and sort of done that. Geez, can I make these numbers work so that I don't have to have 8x18 purlins in a 20-foot bay? And the reality is that we've been over designing all this time, and that we should be looking at the material in this with this light of this new tool, and it makes material sizes significantly more economical. And nobody wants to be dealing with an 8x18 that's 24 feet long. It's just not fun to deal with. If I can make that an 8x10, wow.
So what species are you working with, Mark, primarily?
White pine, eastern white pine, and Doug fir. And Doug fir is God knows where it comes from. It's grain, everything is completely different, load to load.
Ron, Anthony, any comments on this idea of using D245 to develop stresses for new material in new construction that are different from what is in the national design codes?
Well, I agree with Dick. We don't want to go down the path of coming up with another grade. I actually did that in Switzerland, and they had grades at that time, grades 1, 2, and 3. We actually came up with a grade 0, and everybody thought it was ridiculous. So I think Dick's right. We stay within whatever standards we deal with. But here's what I do when I have a project that I need higher design values because the engineer or the architect has selected a particular species and the NDS does not give us the values that we need, then I will specify, I want this to be, let's say it's the 6x12. The 6x12 timbers shall be Douglas fir Select Structural. However, no knot on the wide face will exceed 1.5 inches. And then I take the bump that's allowed in the tables in D245. So I get the higher design values by using D245, but still from the standpoint of the building official, it's Select Structural. And I just have to argue why I'm allowed to take the bump from D245.
Mm-hmm. And the other one is the moisture content in service. If you know this is inside a conditioned building, wouldn't it make sense if you're, well, and I guess the other question is, if you have RF dry material, radiofrequency vacuum dry material, where the checking and so forth is essentially done, would it make sense to use a dry value and take that increase?
I think you might be pushing that. It really depends. Like, I always assume, yes, the materials are going to dry, but I always assume that they're wet. But if you're talking RF, that might be reasonable. But other ways of looking at it, I think engineering judgment is telling me just there's enough unknowns in this stuff. And you look at the spread on the, what do you call it, the data from the raw data, and there's these, they're not really, really tight spreads. They're huge spreads, and you can end up with some really crappy sticks, even though they look good. And sometimes covering your butt is a good idea.
So, Paul, I would suggest that that's a future activity for the council to take on, because you are correct. I think we could make the argument for that. I wouldn't do that now. I make the argument for the drier timber in an existing building because it's been there 20 years, 50 years, 100 years, and I can argue that the building is in equilibrium, and so I can take that bump for moisture content. If I just have brand new sticks sitting there, they're not in the building yet, I don't really know what that building is going to do. I may know what it's designed to do, but I don't know what it will do. And so I'm reluctant to take that to a building official and say, I want to take a bump without knowing how that timber's performed over time.
That's a future research project for TFEC to fund, is maybe look at RF dry material.
So noted.
My clients can't afford it, so we don't even talk about it.
I think it's important to note that, at least in my practice, I've run into building departments that will not accept this methodology, even though it's in the code. So everybody should be, aware of your building department. Probably more of the larger cities. In my instance, it was the city of Portland. I gave them everything and said, the NDS recognizes this, and they still wouldn't accept it. So just be careful when you try to use this.
Does anybody still have any association with the universities? I know, Dick, you used to be at Wyoming, but you can get some of this stuff done by the universities and then someone get his dissertation out of it. That'd be a wonderful thing. Budget might be
the challenge there is graduate students aren't free, and the budgets that the Engineering Council have are really modest compared to what the National Science Foundation or some other granting agency can provide. So although it's certainly worthwhile, we're also a niche market, so it makes it much more difficult to grab the attention of the granting agencies compared to the bigger impact studies, for instance, those dealing with seismic performance of concrete and steel structures, that sort of thing.
The TFEC is open to any bequeathments or donations that anyone is willing to make. And if you want to give us a big enough number, we'll put your name on a research report and thank you to the end of the time. But that's the true state of things, is these are expensive ventures. And we have some stuff in the pipeline for the money that we've collected. But ideally, yeah, if we could partner with somebody, we would love to take on big projects like this. Yeah. Any other questions? Great. I want to thank everyone for their time and attention. If you haven't, I want to remind you, if you want to get AIA credits, please put your name and your phone number in the chat. And if you're interested in picking up Dick's spreadsheet, a copy of Dick's spreadsheet, put your name and your email address in the chat, and we'll get that stuff taken care of you as soon as we can. It is just for Christmas, and we'll see what we can do about getting both those things sorted for then, but it may take us into early January before we can do that. I want to thank Tom and Dick for their time and their attention and this amazing presentation, and for sharing this knowledge. This has been a real eye-opener for me over the years, and I believe that this is going to fundamentally change the way we as professional engineers and timber framers are going to work with this material and assess this material. And again, I want to thank them both for their hard work, especially so close to Christmas. Thanks, guys.
Yeah, you're most welcome. My pleasure.
Yeah, it was a pleasure.
Thanks, everyone. have a safe holidays, stay safe, and we will catch up in early 2021. We've got some more presentations that are in the pipeline, and we just need to finalize some things, and you'll hear more from us. I want to thank everyone from the TFG staff for helping us put this presentation and getting the word out to a number of the people here who I know aren't TFEC members but are TFG members, and they're always welcome to participate and learn from our